So continuing from where I left off, the strain ellipse is an ellipse that gives a good idea of the distortion within a geologic body. So that's basically just like any circle that, as you change it, it's just a tool that you use to tell how much something has distorted. Like down here, we use them, because a circle is pretty easy to see, because of the simplicity of the shape, that it got squished down. Like if you tried to use like a box or like I don't know, a diamond or something like that, it can be a little bit harder, but with a circle it's pretty easily visualized. So S3 is the greatest stretch, maximum finite stretch. S1 is the least magnitude of extension. So I think that's actually might be backwards, but basically S3 is like, it got squished, and S1 got pulled the most. So we can calibrate the strain ellipse by making its original measurements, whatever they may be, equal to 1 unit. So like 1 meter, 1 foot, 1 notepad length, whatever. That's why it's pretty easy to be accurate with it. So evaluating a strain of lines, this one is pretty useful actually. The evaluating strain of lines. So this line L is above 50 degrees above the x-axis, so counterclockwise, so plus 50 degrees. And line M, which is this line that goes kind of down and to the right, is the reference for angular shear. So this is all just to tell you like different things, but focusing on angular shear right now. So we use line M as a baseline parallel to line L that is in its non-deformed form, and then whenever this strain ellipse gets deformed, so this little area of rock that we put in the ellipse, we're saying that how line ML has changed in relation to M is the angular shear. So as the circle is deformed, we see that the change in degrees is from 50 to 26.5 above, right? So L was 50 degrees above horizontal, now it's 26.5 degrees. And that is not the angular shear. The angular shear is found by looking at M, and the dashed line is parallel to L. So this is the new line that would be parallel to L, and line M is, pretty much it is in the same relation from where it was. Like, it doesn't really change. Line L changes. So it's perpendicular to L, and the change in degrees from M to that dashed line is negative 44.5. So that's going clockwise, so negative 44.5 degrees. That is the angular shear. So therefore, the angular shear is tangent angular shear is equal to lambda, which is negative 9.8. And it's pretty easy to kind of think that to like assume this would be angular shear just because that's the angle that it changed from relation horizontal. But in actuality, it's the difference between the perpendicular lines. That was it right up there. Yep. Okay. So the fundamental strain equations. These ones, it's just, you should probably just go over it in a book. It's this is basically like kind of figuring out what changed and in relation to what. It's like a where's the sentence that says it? It's basically values that describes the change in position, the angular, versus the change in length. So it's like, this is the change in length, this is change in the angular position, and it's just kind of the relation between those two. There's more information on this, which is why I'm not really going over it, and it's more in depth. This is just kind of a quick little thing that I used to like solve some side research and equations that I was doing. So like, if you want to know more about fundamental strain equations, you should probably look into that, separately from these videos. So coaxial and non-coaxial strain. Plane strain, there is no stretch or shortening of material perpendicular to the two-dimensional plane containing minimum and maximum stretch. So no change in the S2 plane. S1 is the one that pretty much goes under the biggest stretch, and S3 is the one that goes under the compression, and S2 is the z-axis that goes straight through the middle. So when there's changes in S1 and S3, there's usually no changes in S2. That's pretty much what this is saying. So the difference between coaxial and non-coaxial strain is coaxial is more of like kind of like the homogeneous strain that we talked about earlier, where here, you know, all these dots are where these particles are in position of this ellipse, and whenever it gets squished down, so this is having stress coming from the tops and the bottom, then, you know, they just kind of get shifted to the left and the right, just spaced in between each other. But because the changes in S1 and S3 are reciprocals of one another, then they're not going to really change in the position. That's why it's coaxial, is because they stay kind of in line. Whereas non-coaxial strain is like pushing something with an uneven amount of force. So then these particles shift in their position. So they're not in the same kind of orientation as they were. So basically this difference between homogeneous and non-homogeneous strain, you know, is kind of similar between coaxial and non-coaxial. Instantaneous versus finite ellipse. So an instantaneous is like, when you think about it, like how far something can move immediately is the instantaneous ellipse, you know, like, and that's usually right in this little area, you know, so the amount of particle may move at any given point in time to attribute to the instantaneous deformation path as a whole. So it's just how something might move on any point, like from position A to B to C to D to E to F. That's instantaneous. And they're usually closest to S1 and S3 lines. So to understand finite, you have to look at non-coaxial. We're going to look at non-coaxial strain. As the strain goes on in the finite ellipse, it's thought to be parallel with the strain, and the instantaneous is parallel with S1. So finite is like the total, you know, like it's going, how much it's going to stretch overall. Yeah. This is important to remember when looking at shear zone formations. That is the angle between, because it may not have reached its finite ellipse, but it has reached its instantaneous. So like this ellipse, right, if I have an ellipse like this and I'm pushing it this way, then this would be its finite ellipse, and like this would be the instantaneous ellipses until it hits finite. So instantaneous, 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 finite. And that's like as it morphs and it forms. See, this would be more of the finite ellipse, and these are more the instantaneous. So that's what I'm talking about with progressive deformation, is that like along this finite, like let's say that this brown line is in the same orientation, it shortens first and then lengthens. So it shortens during its instantaneous forms and then starts to lengthen out after it reaches its finite ellipse. I think that should be good for right now. Yeah, next we'll go over constructive law. Oh no, I guess I'll go over this right now. So this is where my cat lay down on my notepad, is right here. So this is the critical shear stress required for the faulting, and this is the cohesive strength of the bedrock and the tangent of the coefficient of the internal friction of the bedrock times the normal stress. This is the constructive law. So this is basically just saying how much something needs to reach critical shear stress, and that's the cohesive strength, and then you add in the coefficient of internal friction of the bedrock times the normal stress. So the normal stress would be this is the sigma 1 sine theta, which is normal stress. This would be theta up here, and you just kind of, right here is like how much stress is enacting on that point, and to find the shear stress, which is the cosine section of it is sigma 1 cosine theta. And, this is sigma 1 right here. This guy. And that's the shear stress. So that's this one right here would be the normal. But it'd be this one. Sigma 1 sine theta is that. So cohesion is the structural strength of any given material body. So like sand has much less cohesion than concrete does. Like concrete can withstand more force before it, morphs and shapes and forms, and the rock's response to force depends a lot on the cohesion. Like it can be elastic where, just kind of you push down on like this would be elastic where you pull it back, but I can pull this slinky super far, but if I wanted I can push it back into when this force when my tension force is pushed back, it can take its original form, whereas plastic means that like as it drops, as the force pushes down on it, gravity, then it stays in this kind of form, but it doesn't like break or anything like that. But the elasticity is lost at that point, so it'd be like if the slinky couldn't go back to this shape, it was just kind of stuck like this. Viscous is there's no elastic or plastic strength, and the material just kind of flows like water or cake batter or something like that. Like there's no like real going back to original shape. So the distribution of deformation within regions express the interplay of the force fields, stress fields, and strength fields. A balance of force drives interconnected tectonic processes regardless of scale. So it's basically just saying like when you add all of the deformation and everything, you're just kind of figuring out how all of the forces are interacting with this one unit of rock. And I think that's it for today. Oh yeah, I drew a little Yoda and a force equation. That's where my cat got onto my notebook. So yeah, I think that's it for this round.